Welcome class to the Math 1030 support video for Unit 7C, the Law of Large Numbers. So we're going to start by thinking about the theoretical probability for rolling a 6 on a six-sided die. What is the theoretical probability? Well, we just kind of see what it should be when we roll a six-sided die. So we're going to say probability of rolling a 6 on a six-sided die is equal to 1/6 because there's 1 6 on the six-sided die and there's 6 possible other numbers. So we can simplify that to 0.16 repeating. We're going to convert that to a decimal so we can compare them across other experiments or other numbers. Okay, so we're going to study what happens when we roll six-sided dice a lot of times. Okay, so we're gonna roll these six-sided dice 45 times, but we're gonna do it quickly. So we're gonna do 3 dice at a time. Okay, so we'll just go ahead and roll these, and we're gonna keep track of how many 6s show up. Okay, so I'm gonna go ahead and roll these and write down what the answer is. Okay, so that one we got all 5s on the 3 dice. That one we got a 1, a 4, and a 5. And we got 2, 2, and 5. We're getting a lot of 5s here. Okay, there's 4, 5, and 6, and 6. So we got a couple of 6s there. And we have 1, 4, and 6. Okay, we're going to pause here and do part B. Using the first 15 rolls, what is the relative frequency probability of rolling a 6? Okay, so we're going to talk about the theoretical probability and watch the relative frequency probability. Okay, so let's take a look at how to calculate a relative frequency probability. We take what we want here. So then we want 6s. 1, 2, 3. There were 3 6s rolled in 15 rolls here. And so we're going to take 3 6s and we're going to divide it by total rolls. So there's 15 total rolls. That's going to equal 1/3, which is equal to 0.3 repeating. 0.3 repeating. Okay, we're going to continue on, and we're going to do 15 more rolls, so 5 rolls of 3, and we're going to record them in red. Okay, so we have 4, 4, 3. We have 4, 3, 3. We have 6, 1, 3, 6. We have 6, 4, 1. And we have 5, 5, 3. Okay, let's take a look at how many more we have. We're going to do part C now, which says, using the first 30 rolls, what is the relative frequency for probability of rolling 6? Okay, so my first 15 rolls were for part B, and that will be these data here. Now for part C, I'm going to do the 30 rolls total. That's going to use all of these data here. Okay, and we are going to go with how many 6s are there total? Well, there's 3 from the first 15, and there's 2 more from the second 15. So what we have total is we have 5 6s divided by 30 total rolls. Okay, so 5/30 is equal to 1/6. So we're exactly on our theoretical probability. Okay. Now we're going to do 15 more rolls using our dice and record the results. Record them in purple. Okay. 2 more dice. So there's 5, 5, 6. 1, 2, 6. 1, 3, 6. 3, 3, 2. And 3, 6, 6. Okay, so it looks like our last roll was a lot of 6s in there. Probably more than what would normally happen. So I'm going to circle those 6s. And we are actually counting all 45 rolls. So we're going to use all of these data here. Okay, so how many total 6s were rolled out of the 45? So we have 1, 2, 3 green, 4, 5, 6, 7, 8, 9, 10. We have 10 6s rolled. Out of 45 total rolls. Okay, that's equal to 2 out of, so if we divide the numerator and denominator by 5, 2 out of 9, which is equal to 0.2 repeating. Okay. So notice that as we go around, as we do more rolls, the relative frequency probability will hover above and below the theoretical probability. Okay. So if we do more rolls, we'll probably have less 6s in our recording, and then we'll kind of go down a little bit. Okay. This brings to the idea of the law of large numbers. Okay. The law of large numbers. The law of large numbers holds that for a large number of trials, the proportion in which event A occurs is close to the probability. In other words, with a large number of trials, the relative frequency probability approaches the theoretical probability. So if we continue this experiment with more rolls, we will have our relative frequency probability go slightly above and slightly below the theoretical probability. Okay, so we'll approach it with a lot more trials. Okay, so that's our law of large numbers. So we do large numbers of trials, then we will have our relative frequency probability approach our theoretical probability. Okay, so at this point, see 0.3 right here, repeating is above. 0.16 repeating was exactly on. Then we went above a little bit, and then we might go below a little bit, or kind of hover around the exact number for theoretical probability. Next, we're going to move on to another experiment situation, environment. Also in gambling, which depends a lot on probability, is what's called the roulette wheel. Okay, the following diagram is an American roulette wheel, and roulette means little wheel in French. Okay, so we have, as you look at the roulette wheel, we have black numbers and red numbers. Okay, so what we need to do is we need to take a look at also the green 0 and 00 spaces. Okay, so those all factor into our probability. So let's think about the probabilities with this this environment, the roulette wheel. What is the probability of getting a red number on any spin? Okay, so they spin the wheel, and there's like a little ball that goes around. Okay, it goes, and then it lands on a number, like 14. It settles in the number as the wheel spins. And that is the one how the numbers are chosen in the roulette wheel. So what's the probability of getting a red? Okay, so probability of, they're thinking about theoretical probability. Okay, we want the total, or sorry, what we want. Divide by the total. Okay, and in this case, what we want is a red marker. All right, so the total amount of spaces, a red space, a red number over the total amount of numbers. Okay, so let's calculate the total here. The wheel is divided into 8 sections, and in each section we have, well, let's do the halves. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There are 19 spaces for every half, so 19 times 2 is 38. Okay, so we have a total of 38 possible numbers. And how many of them are red? Well, let's go ahead and count. Let's start from the top this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so there's 18. All right, so what we want is we want 18 red spaces. Out of 38 total spaces. Okay, so that is 18 divided by 38, and that's about equal to 0.47. Okay, so that's the probability of getting a red. If patrons in a casino spin the wheel 100,000 times, about how many times will it land on the red? Okay, So we just take our number, that is the probability, multiply it by 1,000. 100,000. Okay. So we take our 0.474 times it by 100,000. And we get 47,400. Okay, so it would be about 44. The red number will come about 47,400 times, but not exactly. Okay, we can expect that to be about that much. Right, so we take our probability for the outcome to be read on one spin, and we multiply that by the number of spins. Okay, and we'll have about how many times we can expect the outcome to be read. Okay, so let's expected value. Let's take another look at a different situation and see what probabilities help. Insurance is a big probability game. What's the probability that you will get sick and the insurance will have to pay money? So that's health insurance. What's the probability that you'll get in a car wreck and insurance company will have to pay out from their money stores? Okay, that's auto insurance. Renter's insurance is what a lot of us have that have apartments. And so the renter's insurance is that you pay them a little bit of money so that they can, so that if something happens to you, then they will pay for that event. They will pay for, if it's like you get robbed, they will pay for to replace your valuables and property. Okay? So you're kind of paying into this system where you might not need the money, but it's there if you do. All right, so let's think about the owner's perspective on renter's insurance. So part I here. 4I. You own an insurance company and sell renter's insurance for $250 a year. In your experience, about 1 in 500 people file a claim for $100,000 during that year. Okay, so about 1 in 500 people might have been robbed or something like that, where they will just make a claim for to be reimbursed for their stuff. If you sell 1,000 policies, what will you expect to make a profit? How much will you expect to make a profit? Okay, so you are selling 1,000 policies for $250. Okay, that's how much money that you're going to get in. And that's called revenue. Okay, so calculate the money coming in. So that's what we're doing here. Calculate the money coming in. Okay. So we sell 1,000 policies. They are sold for $250 each. And money coming in is $250,000. Okay. Now, calculate the total money you expect to pay out based on the probability that the number of people making the claim in that year. We are expecting to pay out maybe 2 people because we have 1 in 500 people claim. Okay, so that's this part right here. 1 in 500 people file a claim. We're going to sell 1,000 policies. So we expect that 2 people will make the $100,000 claim. During this year. Okay, so that would be 2 times 100,000. Which will equal 200,000. Okay. Now we need to calculate the profit or loss. If we have $250,000 coming in and we expect to pay out $200,000 during that year, the profit or loss will be the difference of our income and our outgoing. Yeah, so $250,000 minus $200,000 is equal to $50,000. Okay, so that's the money that you will have to not pay. Okay, so it's positive money. So that means you get a profit. Okay, profit of $50,000, and that's in basic terms how insurance companies work. So what we've been talking about with the roulette wheel and spinning it a bunch of times, and with the renter's insurance example, buying lots of policies and having some of them make claims, is called expected value. Expected value is an average value of the probability of an event given the experiment or observation is repeated many times. Okay. So expected value is an average value of the probability of an event. Given the experiment or observation is repeated many times. Okay. There's a formula for expected value, okay, which is the expected value of the event is equal to the value of event 1 times the probability of event 1. Okay, and you keep adding those together. So we can add the value of event 2 times the probability of event 2. And you keep on going, adding in that fashion. Okay, and when you're done, then you can sum them all up. So let's use the formula to calculate the value, expected value, for one insurance policy. On average, one insurance policy sold in the above example. How much would only one insurance policy make, okay, on average? Now this will be one insurance policy if the policies are sold many times, many policies sold. What would be the average for one insurance policy? That's the expected value. Okay. So we have our expected value for one policy given many are sold. Okay, that's the caveat for all of this stuff, is that you have to sell many of them, and that's what and this is what you'll get on each one. Okay. So for our renter's insurance, we have we will get from our perspective, we will get $250 for every insurance policy. So our positive income will be $250 times one insurance policy. Okay, so that's our goal, is one insurance policy. Okay, so the value of the insurance policy is $250. Okay, so we're doing the value here. That's this one. Value of event one. Event one is like me getting the policy. I sell it to someone, they give me money for it. I multiply by the probability of the event, which is probability of event one, which is 1. The probability of me, because I have the insurance company, getting the policy or getting the money for the policy at $250 is certain. Okay, they've done it, they want to do it, the renter wants to buy insurance, so that's certain. Okay, we're going to add that on to the value of event 2. You can go purple. So the value of event 2. Now the event 2 is, for our insurance policy example, is that the only events that happen besides us getting policies is that we have to pay out for somebody who makes a claim. Say that they get their stuff stolen or something like that. We will have to pay out a certain amount. Now, the value of that is going to be $100,000, but to me, that is going to be a negative $100,000. Okay, so I'm going to add on my second event, which is going to be the minus $100,000, because for me, that is going to be a payout negative to my account. Now, how often does that happen? We're going probability of event 2. In orange is this one. What's the probability of that event happening? Well, according to my experience, that was 1 in 500. So about 1 every 500 customers will do that during any given year, during the duration of the policy. Okay, so the probability is 1 over 500. So again, the value of event 2 is a negative $100,000 to me, and the probability that will happen during the year is 1 out of 500. Okay. Now, the expected value for one insurance policy is going to be the simplify this math here, and we'll find that. So that's going to equal $250, because $250 times 1 is $250. I'm going to add that on to whatever $100,000 is, divided by 500, and I get that is 200. So we'll subtract off for 200, because it's negative $100,000. And then the expected value for each insurance policy will be $50. Okay. So if I sell 100,000 policies, then I'll expect to make 100,000 times 50. If I sell 1,000,000 policies, then I'll make 1,000,000 times 50. Okay, so that's the utility of expected value. In this next example, we're going to look at a lottery. Suppose there's a lottery that plays 3 games. Each ticket for all 3 of the games will sell for $1. All tickets sell for $1. If the ticket could be a $5 game, where 1 in 100 tickets pays you $5. Okay? So 1 in 100 tickets pays you $5. There's a $1,000 game, where 1 in 1,000 tickets pays you $1,000. And there's a $1 million game, where 1 in 10 million tickets pays you $1 million. What is the expected value for playing this lottery? Okay, so we're going to play all the games. We just buy random tickets from each game. They're all $1. And we're going to calculate the expected value. All right, so the expected value Okay, so what we're doing is we're calculating the expected value to win on this game if I play it a bunch of times. Remember, expected value on one ticket So the expected value for one ticket given many are purchased. Okay, so what is that going to equal? All right, so we need to just take each of the games one at a time and see what the expected value would be, which means we take the value of the game multiplied by the probability of you winning. Okay, so but first of all, the first event that happens is you buying a ticket. Okay, so for each ticket, you will have to pay $1. So for you, in your perspective, you'll be losing $1. That's the value of the event. And the probability is going to be 1 because that's certain that you will buy that ticket. Okay, so this is, again, expected value, for one ticket. Okay, so we will buy the ticket. So our expected cost will be $1 for that ticket. So that's certain. So that's why the probability is 1. Now let's go ahead and add up the expected values of playing the game. So what's the potential winnings on this ticket? Well, and the chances that you will win. That's what we have to consider. So we're going to make it a math equation. So we're going to add on the $5 game. So we're going to buy a bunch of tickets, and it could be the $5 game one. The expected value of the event is $5, and the chance of winning it is 1 out of 100. Okay. So the next type of ticket is the $1,000 game. So you could win $1,000. That's your value. To you, it could be plus $1,000, positive $1,000. But the chances are 1 in 100,000 tickets will have that. Okay. Now I'm going to add on the $1 million game. So you have $1 million that you could win, positive to you, but there's 1 in 10 million chance of getting it. Okay. So we add all of these up. So let's go ahead and calculate each one, and we'll add them up. So negative $1 times 1 is going to be negative $1, or negative 1, plus, now 5 times 1 over 100, or 5 divided by 100, is 0.05, plus 1 divided by 100, $1,000 times 1 divided by 100,000. So that's 0.01. And 1 million times 1 over 10 million, which is 1 million divided by 10 million, is 0.1. Okay. And so we add them all up, and we get, let me go ahead and make this adjustment here. Okay, when you add up $1, negative $1 plus 5 cents plus 1 cent plus 10 cents, you actually get a negative 80.84. Okay, so that's our expected value for how much we will get on a ticket. Notice that the chance, if you do out of 100, 80% chance of losing money. Well, it'll be 84 cents that you'll probably lose. Okay, so if you play it a whole bunch of times, like 1,000 times in part B, how much money should we win or expect to win or lose? Okay, so you take your expected value times that by 1,000. So you bought 1,000 random tickets. Some might win, but you just need to expect to lose $840. Okay. So if you buy 1,000 tickets, you're investing $1,000 into this game, and you'll probably lose $840 of it. Okay, so that's the expected value. Notice that lottery is a form of gambling, and usually with gambling, most of the time, and pretty much all the time, you, the participant, the gambler, will probably lose. Okay, The games are designed so that you can lose. Notice that this, if you look at these numbers here for the lottery example, you will probably lose. Okay, with the last part of this video, we're going to talk about the gambler's fallacy. The gambler's fallacy is a mistaken belief that a streak of bad luck makes a person do, quote unquote, for a streak of good luck, or vice versa, that a streak of good luck will continue or bad luck will continue. Okay, that's what the gambler's fallacy is. So it is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. Okay, so that's the main idea for it. Or you can think of it as that a streak of good or bad luck will continue. Okay. Now, what is an example of a gambler's fallacy? So if you play a game where you get $1 for heads and lose $1 for tails, okay. So we're going to start out, this example, we're going to actually do it with the coin toss in number 8. If you play a game where you get $1 for heads coin toss test. Yeah, that's the game, is a toss one coin. So you get $1 for heads and lose $1 for tails. Okay. And you have heads, tails, 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 tails. You have this so far. Then you are due for a heads. Okay. So because there is a 50-50 chance of getting tails again. Heads are not really due. Heads cannot be expected. Cannot be guaranteed. Okay. So that's what gambler's fallacy is. Let's go ahead and test it with this coin toss game. So we're going to play coin toss, and we're going to toss a coin 10 times. I'm going ahead and do that. You can go ahead and do that with your handout and see what the results are. Okay. So here's my first toss is a tails. Heads. Heads. Tails. Heads. Tails. Heads. Heads. Another heads. And another heads. All right. Now, I tossed a coin 10 times. How much money am I winning or losing at this point? So let's count up our heads. Heads are 1, 2, 3, 4, 5, 6, 7. Awesome. 7, 7, 7. So we have 7 of them. So we've won $7. Okay, so $7 won. Tails, there's $3 lost. Okay, which is okay. I'm still winning, right? So my net is $4. So positive $4. All right, so let's go ahead and toss the coin 10 more times and see how this gambler's fallacy might work. Tails. 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 Okay, so I might have thought it might have been due for heads, but I got 4 tails now. 5 tails. 6 tails. 7 tails. See, notice that I'm still have the same chance to get tails. Here's a heads. And another tails. And a heads. Okay, so I got lots of tails that time. Let's see how much money we're winning or losing now. So we're going to count our heads. And there are 2 heads. Okay, so since I've tossed it 10 more times, I have 2 heads. $2 won. Tails must be 8. Lost. So my net for this round of 10 is going to be negative $6. Okay? Negative $6. And so altogether, I have $4 plus the negative $6. That's going to equal negative $2. Okay. So I'm down in the negative. How many heads would I need in the next 10 tosses to break even after 30 tosses? Okay. So what I need to do is I'm going to think about what I did in the first 20 tosses. Okay. And we'll ask the question again. In the first 20 tosses, I got, so we got two heads, 7 heads, 9 heads. Okay, I got 9 heads and 11 tails. Okay, 8 and 3 makes 11. 9 heads and 11 tails. To break even at 30 tosses, which means that I would need 15 heads and 15 tails, I would need we need 9 to 15 makes 6 heads, and from 11 to 15 is 4 tails. Okay. Which is likely. Suppose that still behind after 30 tosses, you decide to keep playing because you're due for a winning streak. Explain how this belief would illustrate the gambler's fallacy. Okay. So if I was losing, I cannot expect to get several heads in a row to have a winning streak. If I was losing, which I am, I still cannot expect to get several heads in a row to have a winning streak. Because the probability for each toss is 0.5. Okay? It's half and half, 50-50. Okay, look at what happened in round number 2. I was up $4. But in round number 2, I got 1, 2, 3, 4, 5, 6, 7 tails in a row. That just plummeted my totals. Oh, 8 tails in a row, sorry. 8 tails, and that just plummeted. 7 tails in a row, and a total of 8 tails. So that plummeted my net to be negative $6. Okay. So cannot count on being due for heads. Okay. It could be just tails, tails, tails. Okay. Depending on how much you play. Okay. So that's our video. Please let me know if you have any questions.